Hello, and welcome to the second video in this series on the development of the theory of acids and bases. In a previous video, we saw the development of the linguistics of classifications of acids and bases and learned that a scientist named Svante Arrhenius was the first person to quantitatively look at these things. Arrhenius was the first one to actually quantify what is an acid and what is a base. He found that acids were salts that donated H plus in water, and bases were salts that donated hydroxide ions to water. He further noticed something else. Most people thought of things as either being soluble or insoluble. Arrhenius was the first one to determine that some things dissolved completely in water and were strong electrolytes. However, everything has some degree of solubility, and weak electrolytes exist in equilibrium. He defined the strong acids as HCl, HBr, HI, HNO3, HClO4, and H2SO4, and the 7 strong bases as the 5 group 1 hydroxides, plus strontium and barium hydroxide. People then, with a start on what an acid or a base was, continued their research. Specifically, 2 individuals working independently, Johannes Bronsted and Thomas Lowry, developed their own theory. Essentially, they agreed with Arrhenius that solutions could be either strong and dissolve completely, or weak and exist in equilibrium. However, they had a disagreement on his definitions of acids and bases. They simply found that it was too complicated and restrictive. So in a very short period of time, the theories of acids and bases were evolving. Arrhenius, Bronsted, and Lowry both agreed that electrolytes could either be strong or weak, dissolving or existing in equilibrium. However, they differed on their definitions of acids and bases. Arrhenius said that an acid was anything that donates an H plus ion to solution, and a base donates an OH minus ion to solution. Bronsted and Lowry individually came to a conclusion that was much simpler. They agreed with Arrhenius that an acid donated H plus, but stated a base was something that accepted an H plus. They basically looked at acid-base chemistry as a game of give and take. Acids give H pluses, bases take them. Not long after, the theory was later developed and expanded by Gilbert Lewis. Lewis is most famous for developing the Lewis structures. As you may know, in a Lewis structure, you envision what a molecule looks like by creating the bonds, where a bond is 2 shared electrons, and the point is to have all atoms reach a noble gas configuration in the number of electrons equaling the nearest noble gas, which is called an octet, as noble gases are in group 8. As he was developing the structures, Lewis started looking very closely at what a molecule looked like. For instance, he noticed that on ammonia, you have an unshared pair of electrons. Electrons obviously have a negative charge, and Lewis posited that negatives attract positives. Therefore, his definition of acids and bases was as follows. An acid was anything that can accept a pair of electrons. This is much broader, as it will be anything with a positive charge. Not only an H plus, but a positive metal cation can exist in water. A base, on the other hand, was anything that could donate a pair of electrons. Again, an anion, such as OH minus, can still act as a base, or any other anion. Also, anything like ammonia with a lone unshared pair of electrons can actually act as a base under the Lewis structure. So, when one looks at the development of acid-base theory, it seems like there are 3 different ways of looking at it. In actuality, it's a continuum of understanding that becomes more inclusive. All are correct. Arrhenius and Bronsted Lowry both agreed that an acid donates an H+. Lewis realized that any positive ion can be attracted to a pair of electrons. Therefore, not only is an H+ an acid, but any metal cation. Bases, Arrhenius started with the simplest case for strong bases, which donate OH-. Bronsted and Lowry figured that other things could actually act as bases. Anything that would accept an H+ would be a base. Again, Lewis expanded and refined that by concluding anything that accepts a positive has to be a negative. So anything that's an anion with a negative charge, including OH-, or anything with an unshared pair of electrons can act as a base. When looking at weak electrolytes and acid-base reactions, they exist in equilibrium. So if I have some given base, HA, and I put it in water, acids donate protons. So H2O becomes H3O+. After losing the proton, HA becomes an A-. This reaction also works in reverse. The H3O+ will give the proton back to the A- to go back to being water, and the A- with the HA with the A- becomes HA. Since you are in equilibrium, this reaction has an equilibrium constant of products over reactants. In this case, it is called the acid dissociation constant, with the lowercase a conveniently telling you that you're looking at an acid. Water is the solvent, so it does not show up in the equation. So you have Ka is H3O+ concentration times A- concentration over HA. Similarly, according to Bronsted and Lowry, a weak base is anything that can accept a proton in solution. So if I have A- sitting in water, it will take an H+, and the H2O will turn to OH-, where the H+ plus the A- become HA. Once again, this reaction will work in reverse, where the HA gives a proton to the OH-, reconstituting the water and leaving you with an A-. This equilibrium is defined by something called the base dissociation constant with a lowercase b, to let you know you're looking at a base. Again, the solvent water is not included, so Kb is the concentration of HA times the concentration of OH- over the concentration of A-. There are several important things to note in these simple equilibria. For example, in the first case, HA is giving away a proton, and it's giving it to water. That makes HA an acid. Water is acting as a base. In the second case, H2O is giving the proton to A-. That makes water the acid. So the first point, new word for the day, water is amphoteric. One of the reasons why water is essential for life is that it can act either as an acid or a base. Second thing to notice, HA, the acid on the right, turns into A-, the base on the left. A- turns into HA, the acid. When water is a base, it turns into H3O+, which is an acid. Or when H2O is acting as an acid, it turns into OH- as a base. Second important thing to note, therefore, is that weak acids and bases exist in what are called conjugate pairs. If something is a weak acid on the left-hand side of the reaction, it will turn into a weak base on the right, and vice versa. If it's a weak base on the left, it turns into the conjugate weak acid on the right. Several other things occur. If one looks at the of a weak acid, HA, and its conjugate weak base, A minus. HA, for simplicity's sake, exists in equilibrium with H plus and A minus, giving a value of an A minus exists in equilibrium with OH minus and HA in water. If I go with Hess's law and I add these two reactions together, you'll note HA is showing up on both sides of the equation. Also, A minus is showing up on both sides of the equation. What one is left with is H2O in equilibrium with H plus and OH minus. This is another reason why water is essential for life. It is actually chemically active. Water exists in equilibrium. A fourth useful thing can be gleaned from Hess's law. Each of these equilibria are defined by an equilibrium constant. So water has an equilibrium constant, Kw, H plus times OH minus times 1 times 10 to the minus 14th. If I look, my weak acid had an equilibrium constant of H plus A minus over HA. Conjugate base, again ignoring the solvent water, is HaOH minus over A minus. Applying Hess's law, if I am adding the reactions, that means I am multiplying the equilibria. The result of that, if I multiply these together, A minuses cancel, HAs cancel, and I am left with H plus times OH minus. So, another very useful fact, for any conjugate acid-base pair, Ka times Kb is equal to the water dissociation constant Kw, 1 times 10 to the minus 14th. This means out of the thousands of weak acids and weak bases, one only needs to know Ka in order to find Kb, or vice versa. Finally, the water dissociation constant also allows something to develop something very useful. It stands to reason if an acid donates H plus and a base donates OH minus according to Arhennius, if I have a neutral solution, the concentrations of H plus and OH minus are going to be equal. If they are equal, Kw is equal to x times x is 1 times 10 to the minus 14th, or x squared. So, for a neutral solution, the concentration of H plus would be 1 times 10 to the minus 7th molar. If I have an acid, it stands to reason I have more H plus than OH minus, so the concentration of H plus is greater than 10 to the minus 7th molar. For a basic concentration, a basic solution rather, the concentration of H plus is less than OH minus, or less times 10 to the minus 7th molar. This allows for a very useful tool that you've probably heard of, the concept of pH. Very simply, pH is defined as the negative base 10 logarithm of the concentration of H plus. As an aside in general, as you study chemistry, The lowercase p denotes taking the negative base 10 log. In other words, p of x will equal the negative log of x. So a neutral solution is going to have a pH of 7. An acid with a concentration closer to 0 is going to have a pH of less than 7. And a base is going to have a pH of greater than 7. And as mentioned, anytime you see the letter P, P of x simply means the negative base 10 log of x. So there are 6 things to remember of acid-base solutions. First is water itself. It can act as either an acid or a base. It exists in equilibrium and has its own equilibrium constant. All acids and bases only act as acids and bases when they are in water. If I have a weak acid, it will exist in equilibrium with its conjugate weak base. And for any of these pairs, Ka times Kb is going to be equal to the water dissociation constant. The pH scale gives one a simple way of noticing what one is looking at. A pH of 7 is a neutral solution, less than 7 is an acid, and greater than 7 is a base. I hope you found this video useful and enjoyable, and we'll go into further detail on acid-base chemistry in the next video in this series, which is linked in the description below. Thank you for listening.